All right, welcome. You know, when we talk about infectious diarrhea, it's really not a single disease. At the cellular level, it's actually a battle fought on multiple fronts. So today we're kicking off a two-part analysis into the fundamental mechanisms that are really driving it. In this first explainer, we are going deep, focusing on the two main biochemical processes, what we call the secretory and osmotic shifts. We'll get to the inflammatory mechanisms and all that in part two. So here's our game plan. We're going to start by really defining the core problem. Then we'll dive straight into the secretory and osmotic mechanisms, put them head-to-head to see the differences, and wrap up with why all this molecular detail is so critical for clinical reasoning. Okay, let's get into it. From a pathophysiological view, diarrhea is so much more than a symptom. It really represents a fundamental failure of the intestinal epithelium to maintain this incredibly delicate balance between absorption and secretion. Understanding that balance, that's our real starting point. Now let's explore our first mechanism. I want you to think of this one as a cellular heist. You've got a toxin that actively hijacks an intestinal cell's internal machinery, turning it against the body, and it does all this without causing any direct structural damage. It's pretty sneaky. So this heist, it's not chaotic. It unfolds as a super precise, six-step molecular cascade. It's like a domino effect, right? It all starts with one single binding event on the cell's surface, and it ends in this catastrophic, uncontrolled flood of fluid and electrolytes right into the gut. The actual biochemical sabotage at the very heart of this heist is a process called ADP ribosylation. This is the key move. It targets the GS-alpha protein, a crucial signaling molecule. And by inactivating its internal off switch, the toxin basically just glues the cell's secretory gas pedal straight to the floor. There's no turning back. So here's the crucial point, the real kicker. The cell isn't destroyed. It's not invaded or killed. It's just subverted. It's been completely reprogrammed into this powerful, nonstop secretion pump that just pours and pours isotonic fluid into the gut. All right, let's switch gears and turn to our second mechanism. This one is less of a clever heist and really more of a system failure. It's driven by actual physical damage to the gut's digestive machinery. So what's actually failing here? Well, the core problem is the destruction, or what we call the enzymatic brush border depletion. We're talking about the key proteins responsible for digesting complex carbohydrates. When they're gone, the whole system just breaks down. And this really shows you what's happening. On the left, you see a healthy gut. See how it has low solutes in the lumen? It's absorbing water efficiently. But look at the right. With the buildup of all those undigested carbs, you get a high osmolarity lumen. This creates a powerful osmotic gradient leading to what's called solute-driven water efflux. It just passively pulls water right into the intestine. This whole process is driven purely by physics, which is a really stark contrast to that active secretion we just saw. And this leads to a critical distinguishing feature. If you remove the osmotic load from food, if the patient fasts, the diarrhea stops. And that is a huge diagnostic clue. Okay, so now let's bring these two very different mechanisms together for a little head-to-head comparison. This showdown is really going to solidify how different they are at every single level, from what kicks them off to what you see clinically. This table just lays it all out, doesn't it? The secretory mechanism is an active process, a toxin hijacking a perfectly intact cell. Meanwhile, the osmotic mechanism is passive, started by damage to the cell's brush border. The drivers are totally different, ions versus solutes, and of course, that effect of fasting is a major differentiator. By the way, if you find these custom medical videos useful, please like and subscribe. It helps us make more just for you. So you might be thinking, okay, this is some deep biochemistry. Why does it really matter? Well, because understanding these molecular events isn't just an academic exercise. It is the direct link between that invisible world of the cell and the very visible world of clinical practice. And that brings us to the most important question of this whole explainer. What is the ultimate takeaway here? Why do we spend all this time down at the cellular level? Here it is, the bottom line. The way diarrhea presents clinically is dictated by these underlying cellular events. A secretory process is going to look, feel, and behave totally differently than an osmotic one. So mastering the why, the biochemistry, is the absolute foundation for understanding the what that you're going to see in your patient.
All right, so continuing our deep dive into diarrheal syndromes, we're now going to get into inflammatory necrosis. And this is really cool, a super powerful diagnostic tool that's going to make your clinical reasoning so much sharper, the anatomical localization principle. Let's jump right in.
Yeah, have you ever really stopped to think about this? It's a fundamental clinical mystery. I mean, you get a patient with cholera, and they can be losing like 20 liters of fluid a day. It's just a flood. But then you get a patient with shigellosis, and they're passing these tiny, agonizingly frequent bloody stools. We call them both diarrhea, right? But clinically, they are on completely different planets. So why? What is going on there? That's the exact question we are going to crack today.
And the answer, and this is so elegantly simple, it all comes down to one single thing: location. Where in the gut is the battle actually taking place? This simple idea is what we call the anatomical localization principle, and believe me, it is your key to unlocking the patient's story from the very first sentence they speak.
And look, this isn't just some vague guideline. It is incredibly definitive. The source material puts it perfectly. The location of the disease predicts the clinical syndrome with near-perfect accuracy. So don't think of this as a helpful hint. Now, think of it as a foundational rule, a law of clinical reasoning in gastroenterology. It's that reliable. Now, to really grasp this principle, you have to understand that the small and large intestines are two completely different worlds. Seriously, they are designed for totally different jobs, and they react to an attack in completely different ways. So let's put them side by side and see what that looks like. Okay, so let's break this down. First up, the small bowel. You've got to appreciate that this thing is an enormous absorptive surface. I mean, think about the jejunum. Its surface area is basically the size of a tennis court. It's built to just soak up massive amounts of fluid. So when a pathogen comes in and just overwhelms that system, what happens? You get a catastrophic flood. That's the massive watery diarrhea. The pain? It's usually kind of vague, felt around the belly button. Now contrast that with the large bowel, say the sigmoid colon. Its job isn't mass absorption. It's to do the finishing touches, consolidate stool, absorb that last bit of water. So when it gets inflamed and ulcerated, it completely fails at its job. Instead, it bleeds, it oozes mucus, and the inflamed rectal wall starts sending all these false signals to the brain, creating that painful, gotta-go-now urgency we call tenesmus. And that's exactly why the stools are small, frequent, and bloody. Two different organs, two totally different responses.
So we've got the where down. We know the location matters. Now let's explore the how. How does this damage actually happen? Because when these invasive pathogens get into the gut wall, it's not just about the toxins they release. The real damage comes from the absolutely scorched earth defensive response that our own immune system unleashes.
Think of this as the playbook for invasive diarrhea. Step 1, the bad guy, the pathogen, breaches the wall. That immediately sounds the alarm. Infected cells start pumping out powerful chemical signals, these pro-inflammatory cytokines like IL-8 and TNF-alpha. These things are basically the air raid sirens of the immune system, screaming for backup. And that backup arrives in the form of neutrophils. They flood the area ready for a fight. But here's the problem. Neutrophils are blunt instruments. They're the sledgehammers. They release all these destructive enzymes and reactive oxygen species that, yeah, they kill the pathogens, but they also cause massive collateral damage, just shredding the mucosal architecture itself. And that is what leads to the ulcers and the bleeding. So here's the crucial point. That dysenteric stool, the classic bloody mucoid stool you see in something like shigellosis, it's essentially the debris of this battle. It's not just fluid loss. No, you are seeing the actual tissue of the gut wall being shed. It's got blood from the ulcers, mucus from irritated goblet cells, and just huge numbers of leukocytes, which are basically pus cells. You are literally seeing the evidence of an inflammatory war right there in the stool sample.
Just a quick pause here for a clinical pearl. We really hope these deep dives into pathophysiology are helping you out in your practice. If they are, please consider hitting that like and subscribe button. It really helps us make more custom content like this just for you. Okay, now let's move on and put all of this together.
All right, this is where we bring it all home. We have the location, small bowel versus large bowel, and we have the mechanism, that intense inflammation and mucosal destruction. So how do these two ideas combine to create the clinical picture you actually see at the bedside?
Think of this as your clinical cheat sheet. It's so direct. A patient describes massive, watery diarrhea. Your brain should immediately go, bing, small bowel pathology. It's a problem of overwhelmed absorption. They come in describing small, bloody stools with painful urgency. Your mind should instantly pivot. That's the large bowel, a site of inflammatory destruction. Periumbilical cramps? That points right to the small bowel's pain referral pattern. Tenesmus and urgency, that's the inflamed rectum screaming that it's full. Every single symptom is a clue, a breadcrumb leading you directly to the anatomical location of the fight.
And I really want to end with this because it's the most important takeaway from this whole thing. When you truly understand pathophysiology, you're not just memorizing a list of facts. You're building a powerful mental framework for clinical reasoning. It means that from the very first moment a patient starts describing their stool to you, you already have a good idea of what's going on. You know if you're dealing with a secretory process in the small bowel or an invasive war in the colon. And that's not just knowledge, that is real clinical power.